Good evening, everyone. I'm Anish Ambekar, PMR of PhD candidate in Aerospace Engineering, ISC Bengaluru. Welcome to this week's meeting for the live interaction session for the NPTEL course, Dynamic Behavior of Materials. The course code is NOC24ME102. In this week, we'll be discussing the content covered in week 9 of the course, which particularly includes phase transformations under shockwave passage in its relation to Rankine Unit was. What happens to materials exactly under phase transformation? And another thing being the chemical reactions which may occur during shockwave passage. So, phase transformations, right? Usually, shock waves will have a very small duration. Shock wave, I write SHW for short, will have very small duration, which means that whatever processes that will occur uh, inside the medium, they tend to be non-equilibrium. They happen without equilibrium point being achieved at each state. So, non-equilibrium processes or irreversible processes dominate dominate inside the material. So, analysis doing this way using non-equilibrium processes is particularly hard. So, we make a very simplified analysis. So, we do a simplified analysis which assuming all processes be equilibrium processes. So, it's important that where uh, in when we do a thermodynamic analysis, we typically will be we will typically only be studying processes as equilibrium processes in this context because non-equilibrium processes are harder to model. So suppose we are interested in plotting a PV isotherm, pressure volume isotherm, or phase transformation. Phase transformation, I'll write in short as PHT here on forward. So if I have to plot a PV isotherm, P, this is V, right? And there will be some volume associated V1 and V2 corresponding to the onset of each phase. So you would have an isotherm going like right. So this is how a PV isotherm for a phase transformation process would look like. And we've already seen in previous class that from the Clausius Clapeyron equation of phase transformation. So while deriving this equation, we assumed reversible processes. So you have dp by dt equal to delta S by delta V. So this gives us how the two-phase boundary between say, pressure and temperature, how that boundary varies as a function of change in entropy and change in volume across the phase transformation process. So we take two cases. Case one, here there is a reduction in the volume during phase transformation as well as a reduction in entropy, which means from the Clausius Clapeyron equation we will have dp by dt to be positive. What this tells us is as the isotherm, as the temperature at which we are plotting isotherm increases, your requisite pressure required for the material to undergo phase transformation also increases. They both follow the same trend. If I have to plot it in a 3D plot, pressure versus volume versus temperature. Right. So what I would have is this portion is the straight line between pressure volume. These straight lines that I'm drawing are basically so each of these isotherm is, you can think of it as plotted along a, a PV, a temperature cross section, and then it is plotted on the PV plane. So I just shade this two phase region. This is my two phase region. Both phases can simultaneously exist. And what we see here is if I write temperatures as T1, T2, and T3, if I see how the transformation pressure varies, it will be a line parallel to temperature axis T1, T2, T3. Then we have this relation that T1 less than T2 less than T3 implies T1 less than T2 less than T3. Phase transformation pressure increases with temperature. If I, so this is how it looks as a 3D plot. What we are interested in trying to see how the uh, Rankine-Huguenot curve looks like. So Rankine-Huguenot curve, remember that shock wave is passing through the material in a very short duration of time, which means whatever energy dissipation occurs, it doesn't have a lot of time to move away from the shocked region. So if the pulse is, as the pulse gets thinner and thinner, you can assume that whatever energy is being released locally, that whatever energy is being dissipated locally, that doesn't have anywhere to go within that short duration, which means for thinner and thinner shock pulses, it starts to closely resemble an adiabatic process. So no heat transfer involved. So Rankine-Huguenot curve can be approximated as an adiabatic curve. And how do we plot that adiabatic curve? Suppose it starts with an T and it reaches a point, phase transfer, and then it again goes to another point. So again, this is in 3D. If we take this is my RH. If we take a 2D representation, so this is the PV plot, and here isotherm, if I have to plot, starts looking like this. Think of this as the isotherm, and your Rankine you cannot go. It's just a projection. So you can see that the Rankine unit curve below the phase transformation region is below your say T2 curve isotherm. So it would go something like this, and then at that point it has a discontinuity wherein it overtakes your uh, other. This is your stock area. This point is the onset of transformation, and here you have change in slope of the curve. Okay. Another case we could have, and this is a much rarer case, is if you have a decrease in volume but an increase in entropy, this predicts your transformation pressure to decrease with increase in temperature. So if I have to plot this in the PBT space, you have the mixed phase. This is a mixed phase region, and here you have decreasing temperature T1, T2, T3, P1, P2, P3. Here you have T1 less than T2 less than T3, resulting in P1 greater than T2 greater than T3. And again, if you wish to draw the shock adiabat, it will go something like this. It will go something like this. So you have a curve that goes like this. Right, so I should write this as shock. I take up a projection of the same on a PV plane. What I see is that looks like this. So here I have instead of one, I've got two discontinuities. So, and as we mentioned from the classes question, as space temperature, as space transformation takes place, pressure increases, and thus temperature decreases. This results in another discontinuity in the PV curve. One more part related to phase transformations is that if you have two phases coming together, so if I want to draw it in a PV diagram, how the discontinuity could look like. So suppose this is P2, P1, P0, V0, V1, and V2. So the slope, average slope would look say something like this. Yeah, the average slope would look something like this. Right. So we are concerned here with two shock fronts. So because there is a discontinuity, you could have two shock fronts coming up, and we are concerned about how stable it looks. If I draw pressure versus distance plot, so how the pressure profile looks at different distances inside the material would look something like this. Part of release wave, part shock wave S2 going down, shock wave S1. This shock front will move with velocity US1. Here you have what P0, V0 is the velocities. This shock front will move with velocity US2. The particle velocity is UP2, pressure and volume are P2, V2. Here particle velocity is UP1 and pressure and volume are P1, V1. So with that discontinuity coming up in phase transformation, you can have a two shock fronts, and now our question arises whether such a two shock front system is indeed stable or not. To understand that, we'll first look at the Rayleigh line. We'll first look at stability of two shock front system. What have we got? We require US2 minus UP1, which is the relative velocity of shock front compared to material region 1. This should be less than US1 minus UP1. So basically, a roundabout way of saying that your second shock front should move slower than your first shock front. Only then, and only then, you can have shock, two shock front system being stable. What would happen in the alternate case? If US2 is larger than US1, eventually the second shock front will come catch up with the first shock front and overtake it and move forward. So eventually that is what is seen, and then therefore that becomes a problem. So such a system, such a two shock front system will no longer be stable. Now to determine mathematically what the condition would look like, suppose we first write the equation of Rayleigh's law. So the straight line joining the 2 points of transformation. You have got US1 minus UP0 whole square equal to V0 square times P1 minus P0 upon V0 minus V1. This is for the first shock front US1, and similarly you can write US2 minus UP1 whole square into V1 square V2 minus V1 upon V1 minus V2. Right. Using conservation of mass, we can write US1 minus UP1 is equal to V1 by V0 US1 minus UP0. Similarly, you can write US2 minus UP2 is equal to V2 by V1 US2 minus UP1. Right, so conservation of mass across the shock front. And if you combine these equations, so the Rayleigh slope and so this Rayleigh slope equation and um, conservation of mass equation, what do we see is minus US1 minus UP1 by V1 whole square. So this is basically US1 minus UP0 by V0 whole square, which is nothing but V1 minus V0 upon V1 minus V0. And similarly, you can write US2 minus UP2 by V2 whole square. Negative of that is V2 minus V1 upon V2 minus V1. So this V2 minus V1 upon V2 minus V1 is delta P by delta V, which is nothing but slope. And for the two shock front system, we have this equation US1 uh, US1 minus UP1. So sorry, we are just writing this equation here. So US1 minus UP1 upon V1 whole square. For the two shock front system, we have this condition. So using this, we end up getting US1 minus UP1 by V1 whole square less than US1 minus U, US2 minus US1 minus UP1 by V1 whole square for stability, which implies P1 minus P0 upon V1 minus V0 to be less than P2 minus P1 upon V2 minus V1. So this is the stability condition, and what it means is that whatever your relay line can be drawn before the discontinuity and after the discontinuity connecting those two states, their slopes should be such that the slope of the second part of the relay line should be less than slope of the first part. Now, if we were to theoretically say, if as a theoretical, sorry, not as a theoretical, if we were to extend the pressure volume isotherm, sorry, pressure volume Rankine-Huguenot curve for higher and higher pressures, you can see that eventually there will come a point where your your relay line before the onset of transformation and after the onset of transformation, they both have the same slope. So at that point, your that is the critical limit, so to speak, of pressure. Beyond pressures, beyond this sort of pressure, you would have uh, the slope of sorry, you would have the second shock front, which will start catching up with the first shock front, and therefore the two shock front system will no longer be stable above that particular pressure. So how does one know if this works? People have done experiments where they have say impacted a flyer plate normal to to uh, a projectile normal onto a target that generates some pressure in the target, and if you keep on increasing the velocity of the plate, you first see transformation, onset of transformation, after which you see two different shock waves, two different shock fronts, and then beyond a particular impact velocity, you can see that there's only a single shock front. So forgot the name of that experiment. I think it's there in the lectures as well as the textbook. So the next part was related to how materials undergo phase transformation, rather what happens from a materials point of view when we talk about phase transformation. So we'll take two cases, very popular one. First, the very first reported, which is an alpha to epsilon phase transformation in iron seen at 12.8 GPa. So very high pressure, 12.8 GPa, and the phase transformation is seen. So before that, we first need to plot a unary phase diagram. Unary meaning one component. Phase diagram is basically the different phases involved at different degrees of freedom. Here we are plotting a pressure temperature. Uh, Here we are looking at the pressure temperature diagram. So at different pressures and different temperature, combination of those two. How do we see our zero? This is 1200 zero. And pressure again you have zero. Where here you have 15 and so on. Right. So what happens is there's a triple point somewhere here. What is a triple point? We'll also look at that. This is your gamma, which is FCC. This is your epsilon, which is SCP. This is your alpha, which is PCC. So phase transformation occurs somewhere like this, room low temperatures itself. So this is a unary phase diagram for iron. And another important thing is the Gibbs rule. So Gibbs rule is related to phase transformation. So you have got, it goes like P plus F is equal to C plus 2. C is the number of components. F is number of degrees of freedom. P is number of phases. So since it's a unary phase diagram, C is equal to 1. Unary, only one component. Therefore, your diagram equals to P plus F is equal to 3 for this case. So, if you have a single phase, say like alpha, your P becomes 1, which means F is 3 minus 1 equaling 2. What this means is to achieve your single phase alpha, you can have two possible degrees of freedom, which means you can vary both temperature and pressure to achieve alpha. Same goes for epsilon phase as well as gamma phase. Now coming to the phase boundary which exists between two phases, what you have is, suppose alpha to epsilon is, you can see like it's a curve. So it's on that line in the unary phase diagram, your number of phases becomes 2. So P becomes 2, P plus F is 3, which means F is 1. So, which means there is only 1 degree of freedom. So, provided you are looking at alpha to epsilon phase boundary, alpha epsilon phase boundary, which has two phases, you can only fix 1 degree of freedom. So, if you fix pressure, temperature becomes automatically fixed, and vice versa. Now, at the intersection of those three phases, you have a triple point. A triple point occurs when three phases simultaneously coexist at any particular uh, at a given point. So in our equation, which is P plus F equals 3 for the unary phase diagram of iron, because your number of phases P becomes 3, your F becomes 0. What that means is, the moment you talk about triple point, both pressure and temperature are predetermined. You cannot move around. So that just packs that whole thing up, and this is what we see. In when a shock wave is passing through in alpha to epsilon phase transformation, it is seen that there is a volume reduction associated. Delta V by V naught is equal to minus 6.5%. So there is a 6.5% reduction in volume, and what we also have from the PT diagram, you can see also we see that dP by dt is negative. From the pressure temperature diagram, so I just highlight that. So this is the one that we are interested in. And you can see that as temperature increases or transformation phase, pressure seems to decrease, which means dP by dt is negative. So combining this volume reduction and dP by dt with our Clausius-Capron equation, we get this condition that delta S must be greater than 0, which means entropy increases with phase transformation. So very good example of this entropy increase in phase transformation, and it's a melting of a material wherein it goes from a highly organized solid, like suppose like a crystalline material goes from a highly organized solid to a random to a liquid where your particles are moving randomly. So that is an order to less order, or disorder is probably the wrong word. You go from more order to a less ordered structure there. So that is how it could look like. So we'll now plot our plotting the Rankine humanoid. So this material, what do we see? Pressure V by V naught. So and it starts off at one. And you have pressure in GPA. So we'll go like this. And then there will be a discontinuity somewhere here. It will go like this. Right. So this is the discontinuity. Here, this discontinuity exists because there is a forward transformation from epsilon to alpha at P is equal to 12.8 GPa. Right, so the peak pressure will increase it to 40 and then 40 GPa, and then once it starts unloading, there is another discontinuity that is seen. Discontinuity due to reverse transformation, which goes from epsilon to alpha at pressure equivalent 9.8 GPA. So this is what we see. So what important to note here is that a hysteresis loop is formed alpha to epsilon and then return back from epsilon to alpha. So during this whole process, some debris are left behind. These debris change the residual hardness. What do we know about this? Two ways about the debris. First is if you can have an optical micrograph and look at different cross sections at across different depths, you will see some transformed material as well as untransformed material being left behind inside the process. So some epsilon phase debris may be left around some small islands. And another way was to measure the hardness, which is what Mayers did. Mayers and his group did. So let's have a look at this. Right. So what they did was, say, 4 is all the way till 60 mm. So what they did was they measured the depth, measured the hardness at different depths. They used a plastic explosive, detonated it at the surface of a steel block with a grazing incidence, not normal, so grazing incidence, and the pressure that they achieved at the surface was above 13 GPa, and what that did is it would cause the forward transformation, and then as the shock wave moved deeper and deeper inside the material, we have already looked at attenuation. Peak pressure of the shock wave kept on decreasing, which means that beyond a certain depth, there is no transformation that takes place. So near the surface, there is phase transformation from alpha to epsilon, which after unloading leaves some residual debris. Those residual debris contribute to an increase in hardness of the material very close to the surface where phase transformation has successfully taken place. Whereas as we move deeper and deeper inside the steel block, the peak pressure never crossed that phase transformation pressure threshold, meaning that whatever material was there in alpha BCC that remained the same. So the material beyond a certain depth is unchanged, so there is no change in the hardness of the material. So this is how they, like in an indirect fashion, could see how phase transformation takes place. Another case for materials is a phase transformation between graphite and diamond. Phase transformation at pressures of upwards of rather 2.3 GPa. Again, we'll plot a unary phase diagram. So you would have, so this is not like a linear scale. So what you would have is this portion is graphite. Values are indicative, so maybe up or down. Have to see. This portion is diamond, and there is an intermediate portion which is diamond plus metastable graphite. Right. So what we see here is phase transformation begins 2.3 GPa. Right. And what this results in very small diamonds formed. What these diamonds are is they're typically this phase transformation martensitic phase transformation due to shock wave. It's martensitic, meaning the diamond formed is a hexagonal HCP rather than cubic. Cubic is naturally occurring. Another thing about this diamond is its diameter is usually of the order of hundreds of angstrom, and they can be polycrystalline. So you could have very small diamonds coming up, and they could also be polycrystalline. Not much. So the application rather that it finds is used as a polishing agent. And another important point to notice: phase transformation from graphite to diamond requires quenching, rapid cooling. If rapid cooling is not there, then graphite is reformed. So it's formed again. No phase transformation. So to do this phase transformation, what they do is use copper powder as an annealing agent. Sorry, as not annealing, as quenching medium. Quenching or rapid cooling, sorry. Uh, so what they do in this process is they'll have graphite powder, and inside that graphite powder, they'll also have sufficient amount of copper powder dispersed. And when the shock wave passes through, once it reaches sufficiently high pressure, diamond crystallites uh, can form. But to do so, heat needs to be taken away rapidly. That is done by those copper powders. So this process is used formally by the DuPont company, which produces small uh, polishing agents, diamonds. And okay, and the final section in this week was related to another feature of shock waves, which is chemical reactions. So under shock wave loading, mixtures of powders react and form new compounds. So here usually exothermic reactions are preferred, and the reason to use powders rather is it helps produce higher temperature at the particle interface. So, broadly speaking, you can have two types of chemical reactions. First one being chemical synthesis. Here you could have something of the form XA plus YB giving rise to AXBY. Example of the same is nickel aluminium will form NiXAly. So a lot of such compounds can be found such as NiAl, Ni2Al3 and so on. Another example could be niobium with silicon. Okay, so the second form of reaction that we see is the decomposition reaction. So an example of the same could be copper oxide plus, plus copper oxide, CO or lead oxide giving way to some. Yeah, so both synthesis and decomposition reactions can take place. Uh, Reactions can be initiated by shock waves or they can proceed to completion. What also happens is that the temperature in the material can be increased after passing of shock waves, so that can help in continuing the reaction. So we have three possible scenarios regarding reaction completion or progression. So the first is material is fully reacted within pulse duration. An example of the same would be this is my pulse duration. So if I look at material, so ahead of the pulse, material is unreacted. Behind the pulse, so what we say is some part of the material is partially reacted, other part of the material is totally reacted. You have scenario, the dark part is totally reacted, whereas closer to the front of shock front, you have material which is still being reacting. Ahead of the shock front, material is completely unreacted. Next, next scenario is material is partially reacted. Pressure, distance, shock pulse. Right. So ahead of the shock front, again no reaction. Behind the shock front, again material is no longer completely reacted. So you have some partial reaction happening within the shock pulse. And the third case is material continues reaction after shock wave passes. So within the shock pulse, we are saying that material is only partially reacting, but far behind the shock pulse, material is fully reacted. This is the portion of material that is fully reacted. And then passing of shock pulse only partially reacts the material. Right. So this typically would happen if there is like an exothermic uh, reaction associated, which means that as the pressure increases, reaction starts with release of energy from the exothermic components. The reaction just keeps on continuing. So any reaction is basically it's a complex mechanism. Rather, the mechanics of the reaction is particularly complex. It depends on a large number of factors. It depends on material porosity, particle shape and size. What is your shock pressure, and so on, as well as say your initial condition. Right. Another aspect that we discussed was related to porous materials. So why porous materials are used? These are used in reactions initiating due to higher energy levels being reached. So if you remember our equation of state using Me-Grunesa equation of state, we are evaluated for for powdered materials. How for the case of powdered materials, how the energy balance equation would look like for porous materials. So it was like half of E plus V naught double naught minus V. So this V double naught is has a higher value in status for powders. So which means that you can achieve like higher levels of energy threshold for the same pressure, or for same energy you could have like different pressure values. And if you have a reactive material, energy released has to also be included in the conservation of energy equation. It means your conservation of energy equation ends up looking like, so this is also demonstrated, sorry, evaluated by Myers as well as a couple of other people. Is delta Q, where delta Q is the energy associated with the reaction, which is released. So, okay, so this covers the three important sections that we looked at in this lecture, in this week's lecture. First being the shock, first being the phase transformation under shock wave and how it looks like in the PV diagrams, then discontinuities associated to shock wave front system. Then we looked at a materials perspective, delving into two well-known cases, phase transformation in iron and phase transformation from graphite to diamond. Sorry. And the final part was related to chemical reactions, wherein we looked at how a mixture of powders would come together for a chemical reaction under shock waves, and what kind of reactions we have. We have both synthesis and decomposition. What happens as shock wave progresses inside the material? You could have three different scenarios where either the reaction gets completed within the shock pulse, or it's partially completed, or a third case where it's partially completed within the pulse, but then behind the pulse it reaches completion. So usually some exothermic material would be involved in such a case. And if you have porous materials, they are used particularly in the starting of reaction because higher energy levels can be achieved. And there also you could have higher temperatures because of the interparticular of the powder, your the surfaces interfaces of the powders rubbing against each other. If an exothermic process is involved, there will be some energy release associated, which has been accounted for in our energy balance equation. So this completes what we had for this particular lecture. Uh, if you have any more doubts, you may ask them now. If not, we'll close this lecture.